Hello everybody, welcome into another lesson. So today we are going to talk about graphing rational functions. So in yesterday's lesson we talked about rational functions, about finding your vertical asymptotes, horizontal asymptotes, slant asymptotes, your domain, your range, x-intercepts, y-intercepts, what have you. Today we're going to put all that into practice and we're going to graph these rational functions. So here you have f of x equals 1 over x plus 2. Well, I'm going to say first we go for the vertical asymptote. That of course occurs when you would get a denominator equal to 0. Well, x plus 2 equals 0, that would give you x equals negative 2. So you have a vertical asymptote that's going to be found at x equals negative 2. So let's go ahead and draw the vertical asymptote. That's going to be the physical boundary that this graph cannot cross. Now, as we'll discover sometimes, you can cross horizontal and slant asymptotes, but you can never cross a vertical asymptote. It never works that way. Now, the numerator is less than the degree of the denominator, so it has a default horizontal asymptote at y equals 0. So the horizontal asymptote is going to be at y equals 0. Alright, now what about intercepts? Well, y-intercept occurs when x equals 0. If we did that, you would end up getting a y-intercept at y equals 1/2. So we actually do have a y-intercept at the point 0, 1/2, but there's no x-intercept. If you set this equal to 0, you would get 1 equals 0, which isn't true. So we don't have an x-intercept. Now, last but not least, let's find the domain. And since we have a vertical asymptote at x equals negative 2, that should tell us that our domain, our values for x, can be anything except for x equals negative 2. So the domain in this case would be from negative infinity to negative 2 non-inclusive in union with negative 2 non-inclusive to infinity. I don't think we need to draw the horizontal asymptote because it's literally the whole x-axis at y equals 0. So that's pretty good for that. We can, however, plot that y-intercept at 0, 1/2. That could definitely help us out. There's the y-intercept. Alright, so what's this going to look like? Well, let's take some points here. What about when x equals negative 1? When x equals negative 1, you would get 1 over 1, which is 1. Let's say we took negative 1/2. Well, you would get 1 over 1/2, which would give you 2. And as you see, the further left you go, the further up you're going. Alright, let's do let's make x 1. If x were 1, you would get 1 over 3, which would be down here. X were 2, you get 1 over 4, which is even lower. So you get infinitely closer and closer to that y value of 0, but you never reach it. So the graph is going to look something like this. And now let's go ahead and find x equals negative 3. Well, if x equals negative 3, you get 1 over negative 1, which is negative 1. What about when x is negative 4? You would end up getting negative 1/2. X is negative 5, you get negative 1/3. Alright, let's do x is negative 2.5. You would get 1 over negative 1/2, which would be negative 2. So as you see, the closer you get to x equals negative 2 from the left, it gets infinitely smaller. And then the farther away you get going left, it gets infinitely closer to y equals 0, but never actually reaches it. So the graph of this rational function is going to look something like this. So you can clearly see your horizontal asymptote at y equals 0. Your graph gets infinitely closer and closer to it, but never actually reaches it. And then you also, for your y boundary, it gets infinitely, well, I mean, for your x boundary, it gets infinitely closer to x equals -2, but never actually reaches it. Which should help us identify the range. Your range would end up being from -infinity to 0 non-inclusive, because it doesn't actually equal 0, in union with 0 to infinity non-inclusive. So there's everything about f of x equals 1 over x plus 2. Let's do another rational function in which the degree of the numerator is less than the denominator. Alright, now f of x equals 1 over x minus 6. So we have f of x equals 1 over x minus 6. Well, what's our vertical asymptote? Set x minus 6 equal to 0, you'll get x equals 6. So you have a vertical asymptote located at x equals 6. As a matter of fact, let's go ahead and draw that. Sorry about that nails on the chalkboard sound, everybody, but I'm just trying to draw this vertical asymptote really well. Alright, so there's x equals 6, the vertical asymptote. Now, what about a horizontal asymptote? The degree of the numerator is less than the degree of the denominator, so you have a default horizontal asymptote at y equals 0. Alright, so now what we have here, then we have our horizontal asymptote at y equals 0. Alright, do we have any x-intercepts? No, because if you set 1 over x minus 6 equal to 0, you'll just get 1 equals 0, which isn't true. So this is not going to have an x-intercept. What about a y-intercept? If you set x equal to 0, you would end up getting -1/6. So you actually do have a y-intercept at the point 0, -1/6. Alright, so that's going to pretty much be darn near the x-axis, but up there, almost towards the x-axis. Okay. Now, let's plot some points. Let's put in 7 for x. Well, you would get 1 over 1, which would just give you 1. If we put in 8, you would get 1/2 for your y. You put in 9, you would get 1/3. You see it's getting infinitely closer to 0. If you put in 6.5, you would get 1 over 1/2, which is 2. And you see, once again, it's going upward the further left you go. So your graph is going to look something like this, with everything shifted over that many units. Alright, now, everything's shifted to the right 6 units. Let's put in 5 for x. That would give you a y value of -1. If we put in 4, you would get -1/2. Put in 3, you would get -1/3. Alright, if you put in -5, if you put in 5.5, you get 1 over -1/2, which is -2. So you see, the closer you get to x equals 6 from the right, you're going towards a y value of -infinity. The further left you go, you're going towards a y value of 0, going through the y-intercept there, and that is what your graph would look like. Alright, now let's do one here. We'll actually do one where the degree is less. Let's do 2 more where the degree is less. What if I did this? 1 over x squared. I have 1 over x squared. Well, I'm definitely going to have a vertical asymptote, because if you set x squared equal to 0, you would get x equals 0. So that'd be the entire y-axis. So you'll have a vertical asymptote at x equals 0. Now you would also have a default y-asymptote at y equals 0, because the degree of the numerator is less than that of the denominator. Alright, now let's put what the horizontal asymptote is. That's going to be y equals 0, so I don't think we need to draw the asymptotes. They're pretty well drawn for us on the axes. Alright, now there actually are no intercepts, neither x nor y. Y-intercept, if you put in 0 for x squared, you'd have it undefined, so there is no y-intercept. And you set 1 over x squared equal to 0, you would get 0 equals 1, which is a false statement, so you'll actually have no x-intercept either. Alright, now, what if, let's see here, that tells me that the domain can literally be anything except x equals 0. So the domain would be from negative infinity to 0 non-inclusive, in union with 0 to infinity non-inclusive. 0 non-inclusive to infinity. Alright, let's go ahead and graph this. If I put in 1 for x, well, I'll end up getting a y value of 1. So let's graph that. If I put in 2 for x, I actually get 1/4, which is all the way down here. You see I'm getting infinitely closer to the x-axis. If I put in 1/2 for x, I actually end up getting 1 over 1/4, which is 4. So you see, the further left I go, I'm actually getting closer to infinity. So here's what the graph's going to look like over here. Alright. Now let's put in -1 for x. You actually get +1 for your y value. What if I put in -2 for x? I end up getting +1/4. And as you see, I get closer to my y value of 0. Now, if I put in -1/2 for x, I end up getting 1 over +1/4, which would give me 4. So the further right I go, I'm also going to infinity. So if you have a constant over a quadratic for a rational function, this is roughly what it's going to look like. It'll look a lot like this, which means your range, it doesn't actually reach 0, but you don't have any negative y values, so that means your range is 0 non-inclusive to infinity, because your range doesn't actually hit 0, and it certainly isn't less than 0. Let's do a couple more of these quadratic denominators. It's going to be a little bit different. So let's say, this time I'm just going to change this ever so slightly. I have 1 over x squared plus 1. Well, let's see if we can find a vertical asymptote. This would be when x squared plus 1 equals 0. Well, here's the thing. Does x squared plus 1 in the set of real numbers equal 0? It doesn't. So actually you have no vertical asymptote. There are no vertical asymptotes this time. Alright, now how about horizontal asymptotes? You'll definitely have a horizontal asymptote because the degree of the numerator is less than that of the denominator, so you're only going to have a horizontal asymptote at y equals 0. But you won't have a vertical asymptote because there's no real values of x that you could put in and get 0 in your denominator. You can get imaginary values, but that doesn't work when graphing in the normal coordinate plane. Now, let's see here. What about intercepts? Well, y-intercept, you put in 0 for x, you would get a y-intercept at 0, 1. So we do actually have a y-intercept at the point 0, 1. How about x-intercepts? Set 1 over x squared plus 1 equal to 0, you would get 0 equals 1, which is false. So you don't have an x-intercept. Alright. So if we have no vertical asymptote, what does that mean for the domain? That means your domain is actually the entire set of real numbers. Now before we answer the range question, we might want to graph this. It might be easier. So we know about our horizontal asymptote at y equals 0. We know about our y-intercept at 0, 1. Okay, so why don't we put in 1 for x? If you put in 1 for x, you actually get a y value of 1/2. If you put in 2 for x, you would get a y value of 1/5, which is all the way down here. So you go to the right, you're getting closer and closer to that y equals 0, but you're not actually reaching it. Now, what if I put in -1 for x? Well, that would turn this positive. You'd be back to positive 1/2. What if I put in -2 for x? I would get positive 1/5. And on the left side, it's also getting closer and closer to x equals 0, but it's not actually reaching it. So I get pretty much like a bell-looking curve there. I get basically a bell-looking curve for 1 over x squared plus 1. Which now when we look at the range, your range would literally go from 0 non-inclusive, because it doesn't actually reach 0, it gets close to 0, but notice the highest value in your range is y equals 1. So it would go from 0 non-inclusive to 1 inclusive, because it actually does equal a y value of 1. So that's a little bit different. Alright, let's change this again here. I'll make this easy also. Let's actually make this f of x equals 1 over x squared minus 4. Well, f of x equals 1 over x squared minus 4. Okay, we can definitely factor the denominator, right? This would turn into f of x equals 1 all over x plus 2 times x minus 2. Well, again, vertical asymptotes occur when your denominator equals 0. You have two factors, so if you set each factor equal to 0, you actually have two vertical asymptotes. You have vertical asymptotes that are going to occur whenever x equals either positive or -2. So you have two vertical asymptotes when x equals either positive or -2. So let's draw those out. Again, sorry about the nails on the chalkboard sound. And then let's go to +2. That's your next vertical asymptote. So yes, it is possible that you have more than one vertical asymptote. You will sometimes have that. Now, what about a horizontal asymptote? Well, the degree of the numerator is less than that of the denominator, so you will have a horizontal asymptote at y equals 0. Alright, now what does that tell you about the domain? You can literally have any value of x except for either plus or minus 2. So here's your domain. Your domain would be from -infinity to -2 non-inclusive, in union with -2 non-inclusive to 2 non-inclusive, in union with 2 non-inclusive to infinity. So any numbers except for -2 or +2. Now before we answer the range, let's graph this. And of course, why don't we look at intercepts also? there's not going to be any x-intercepts because you set 1 over x squared minus 4 equal to 0, you get 0 equals 1, which is a false statement. There are no x-intercepts, but what about y-intercepts? Well, if you set x equal to 0, you would get negative 1/4. So you actually do have a y-intercept. That'll occur at the point 0, negative 1/4. So we can definitely plot that at 0, negative 1/4 would be right about there. Okay. Let's start on the left first. So if I put in negative 3 for x, what do I get? I would get 1 over 9 minus 4, which is 1/5. That'd be about right here. What if I put in negative 4 for x? So that would give me 1 over 16 minus 4. That'd give me 1/12. That's even less. So it's getting closer and closer to 0 to the left. And as you can imagine, it's going to go up the further higher you go. Let's go to the right. If I put in positive 3 for x, very much the same thing's going to happen. I'm going to get 1/5. If I put in positive 4, I'll end up getting 1/12, which is even less, and I'll end up getting much the same thing over here. So what about in between negative 2 and 2? What's going to happen there? Well, we know 0, you get the point negative 1/4. So what if I put in negative 1? That'd give me 1 over 1 minus 4. That'd give me negative 1/3, which is about here. And if I put in positive 1, I would get roughly the same thing. And then actually your graph's going to go a lot like this. Your graph's going to look a lot like that in the middle. So you can get some very interesting graphs based on asymptotes you have and intercepts. Now, what does that mean for your range? Notice, okay, in your range, you can get infinitely closer and closer to 0, but you'll never actually reach it. But below the x-axis, the highest value you actually have is negative 1/4. So what's interesting is your range is going to be from negative infinity to negative 1/4 inclusive, because it actually equals negative 1/4. And then you go to all the way to 0 non-inclusive to infinity. So in between negative 1/4 and 0, you don't actually have anything. So sometimes graphing this will help you to answer what your range is. Alright, let's move on to some where you have the same degree in both the numerator and denominator. For example, let's say we had f of x equals 5 plus 2x all over 1 plus x. So f of x equals 5 plus 2x all over 1 plus x. Alright, well, let's look for your vertical asymptote. What is the vertical asymptote? Set 1 plus x equal to 0, you get that x equals negative 1. So you have a vertical asymptote located at the point located at x equals negative 1. So let's go ahead and draw that for good measure. Alright, now what about a horizontal asymptote? Whenever the degree of the numerator is the same as the degree of the denominator, which in this case it is, you just divide leading coefficients. So you would take 2 divided by 1, you would get a horizontal asymptote at y equals 2. So the horizontal asymptote in this case is going to be at y equals 2. All right, so let's draw y equals 2. There is our horizontal asymptote. All right, what about intercepts? Well, if I put in 0 for x to find a y-intercept, I would get 5 over 1, which would end up giving me a y-intercept at 0, 5. So I do have a y-intercept located at 0, 5. So let's go ahead and label that. 4, 5. Here's the y-intercept. All right. Now, what about x-intercepts? Good news is, yes, we are going to have some x-intercepts. If I set 5 plus 2x over 1 plus x equal to 0, that 1 plus x will disappear. You would just have 5 plus 2x equal to 0, which would end up giving you that x equals negative 5 halves. So you have an x-intercept at the point negative 5 halves 0, or negative 2.5 0, however you choose to look at it. So there is going to be your x-intercept. Probably put that in black. Alright, so we got intercepts this time. Now, at the very least, we can identify the domain, because we have a vertical asymptote at x equals negative 1. So that means your domain is everything except x equals negative 1. So the domain is from negative infinity to negative 1 non-inclusive in union with negative 1 non-inclusive to infinity. Alright, let's go ahead and graph, and then we can probably identify the range a little bit easier. So let's put in 1 for x. Well, you would end up getting 7 over 2, which would give you 3.5, which would put you right there. Let's go ahead and put in 2 for x. You would end up getting 9 over 3, which would give you 3. Let's put in 3 for x, so you would end up getting 11 over 4, which would end up being 2 3/4. So you see, you're getting gradually closer and closer to that y equals 2 line. So your graph is going to look a lot like this. It'll get infinitely close to a y value of 2 without actually reaching it. And then the further left you go of that y-intercept, the higher your y values go. Alright, let's go to the left of negative 1. So let's put in negative 2 for x. So you would end up getting 5 minus 4, which would be 1, over negative 1. That would give you a y value of negative 1. Alright, and then let's put in the full-fledged negative 3. 5 minus 6 is negative 1, over 1 minus 3 is negative 2. You would actually end up getting positive 1/2. Let's put in negative 4. So 5 minus 8 is negative 3, over negative 3 would give you positive 1. And as you see, you're getting infinitely closer and closer to y equals 2, but you'll never actually reach it. So your graph is going to look a lot like this. And it almost looks like when we were graphing the degree less than that of the denominator, but it just shifted your horizontal and vertical asymptotes. That's all it's managed to do. So this should tell you something about your range. Your range can be anything except for you don't actually hit a y value of 2. So your range is going to be from negative infinity to 2 non-inclusive in union with 2 non-inclusive to infinity. That's your range. Alright. Let's do a couple more of the same degree, and then we'll actually get into where the degree of the numerator is greater than the degree of the denominator. We still have to get through those today, too. Alright. let's see, we have 1 minus 3x all over 1 minus x. So we have f of x equals 1 minus 3x all over 1 minus x. Well, we can identify the vertical asymptote pretty readily. That's just going to be 1 minus x equals 0. That would give you x equals 1. So you have a vertical asymptote located at x equals 1. So let's go ahead and draw that vertical asymptote. Now, what about a horizontal asymptote? So the degree of the numerator is the same as the degree of the denominator, so divide your leading coefficients. -3 divided by -1 gives you +3. So you're going to have a horizontal asymptote located at y equals 3. So let's go ahead and draw y equals 3 while we're at it also. Alright, so there, both your asymptotes are drawn. Now, let's see, your domain, that's pretty clear that it can be anything except x equals 1. So your domain is going to be from -infinity to 1 non-inclusive in union with 1 non-inclusive to infinity. The range we'll get to in a minute, but what about intercepts, okay? So a y-intercept, set x equal to 0, you would get 1 over 1, which would just give you 1. So you have a y-intercept located at the point 0, 1. Alright, so at 0, 1, that's your y-intercept right there. Now what about an x-intercept, okay? So set this whole thing equal to 0. This would just turn into 1 minus 3x equals 0. So that would give you 3x equals 1, so x would equal 1/3. So you actually do have an x-intercept at the point 1/3, 0. So let's plot our x-intercept at 1/3, 0. That's going to be roughly right there. Alright, there, we got both intercepts plotted. Now, we can probably proceed to graphing. Let's start at the right first. So let's put in 2 for x. If I put in 2, I'll get 1 minus 6, which would end up being -5 over -1. That would actually give me +5, which would go right here. If I put in 3, that would give me 1 minus 9, so that's -8 over -2. That would give me +4. So as you see, I'm starting to come down again. And my graph's going to do something a lot like this. Alright, we know what happens at 0. We know what happens at 1. Why don't we put in -1? So that would give you 1 plus 3 over 1 plus 1. So that would give you 4 over 2, which would actually give you a y value of 2. So as you see, your graph is actually starting to do this number down to the left here, to the left of that vertical asymptote. So there's the graph. Now, what about for your range? Well, it looks like in our range we have anything except for y equals 3, because it gets infinitely closer and closer to y equals 3, but it never actually reaches it. So your range is going to be from -infinity to 3 non-inclusive in union with 3 non-inclusive to infinity. Alright, let's get into some higher degrees where the degree is the same. Alright, so what if, I don't want to do that yet. Perfect. f of x equals x squared all over x squared minus 4. So f of x equals x squared over x squared minus 4. Well, we can actually start with the horizontal asymptote this time. The degree of the numerator is the exact same as the degree of the denominator, so you just take your leading coefficients. 1 divided by 1 gives you 1. So you will have a horizontal asymptote located at y equals 1. So let's go ahead and graph that. That'll be right here at y equals 1. Let's go a little further. Alright, so what about the horizontal? I mean, what about the vertical asymptote? That's when your denominator equals 0. Well, you get that at both x equals plus and minus 2, so you actually have 2 vertical asymptotes this time. That'll occur when x equals both plus and minus 2, so there's 2 vertical asymptotes. Let's go ahead and draw those out so we get a good graph of this. And there's your regular x equals 2. We already did the negative 2. Let's do positive 2. So yes, you are left with 2 verticals and 1 horizontal asymptote. Okay, now what about your domain? Your asymptote, your vertical ones, give it away. Your domain is going to be anything except x equals negative or positive 2. So the domain's from negative infinity to negative 2 non-inclusive, in union with negative 2 non-inclusive to 2 non-inclusive, in union with 2 non-inclusive to infinity. Now, when we go to graph, it'll probably make the range a little more obvious. Okay, so let's find intercepts. We can find the y-intercept when x is 0. And as it turns out, you put in 0 for x, of course you'll get a y value of 0. And if you set this equal to 0, you also get 0. So both your x and y intercepts are at the origin. So both intercepts actually occur at 0, 0 in this case, right at the origin. So we can go ahead and label that. You can plot that point. All right. Let's start at the right. So let's go ahead and put in x equals 3. That would give you 9 over 5. So that would be 1 4/5. Right about there. Let's put in 4. That would give you 16 over 12, which would end up being 1 4/12, or 1 1/3, a little bit lower. Let's put in 5. That'd be 25 over 21. That would be 1 4/21. So that's even lower. So as you see, you're getting infinitely closer and closer to that y value of 1, but you're never actually attaining it. And then the closer you approach x equals 2 from the left, the higher your x values get. Alright, let's go to the left of x equals negative 2. If we put in negative 3, notice you'll get the exact same thing. You would get 9 over 5, which would be 1 4/5. If you put in negative 4, you would get 16 over 12, which would be 1 3/12, so that's a little bit lower. I'm sorry, 1 4/12, 1 1/3. You put in negative 5, you get 25 over 21, which would be 1 4/21. That's even lower. So your graph is really going to do much the same thing as it did on the other side of the other vertical asymptote. Now the big question, what happens in between the 2 vertical asymptotes? We know we have an intercept at 0, 0. So why don't we put in negative 1? If I put in negative 1 for x, what happens? I'll get 1 over negative 3, which would give me negative 1/3. That's about right here. And if I put in positive 1, I would get much the same thing. In fact, my graph is going to do this. which is going to make that range question very interesting. So there's my graph of x squared over x squared minus 4. Now, what about the range? Okay, it would look like our range goes all the way to y equals 1, but look at this middle piece here. The highest part of the range you get is 0, and then it goes to negative infinity. So your range is actually going to be from negative infinity, this time to 0 inclusive, because your range actually does hit 0. But notice your y values don't take on anything between 0 and 1. Your next part of the range is actually all the way up to 1 non-inclusive to infinity, because you get infinitely closer and closer to y equals 1 without actually reaching it. So there's your range. Now let's go on to some graphs where we have a higher degree in the numerator than that of the denominator. All right. So I have f of x equals 2x squared plus 1 over x. F of x equals 2x squared plus 1 over x. Well, the vertical asymptote is still going to hold, because when you look at this, x doesn't factor into either part of the numerator. So you'll have a vertical asymptote at x equals 0. That much is true. So x equals 0 is your vertical asymptote. However, the degree of your numerator is greater than the degree of your denominator, which means you don't have a horizontal asymptote. There is no horizontal asymptote. However, if the degree of your numerator is exactly 1 degree greater than that of the denominator, you instead have a slant asymptote. So we need to do some division here real quick. Let's take that 2x squared plus 1 divided by x. So 2x squared plus 0x plus 1, really divided by x plus 0. X goes into 2x squared 2x times, so you would get 2x squared plus 0x. So do some subtraction here. You would literally end up getting 0. Then you have that remainder of 1. You don't worry about the remainder. What you get that's not the remainder is your slant asymptote. So you actually have a slant asymptote through the line y equals 2x. That would be your slant asymptote. So let's go ahead and plot that. That's going to make this graph very interesting. So let's see, 0, 0, 1, 2, 2, 4, 3, 6, 4, 8, 5, 10, okay. I'm just trying to carefully plot this vertical asymptote so we get an accurate graph. Negative 1, negative 2, negative 2, negative 4, negative 3, negative 6, negative 4, negative 8, negative 5, negative 10. Okay. So now you see that slant asymptote in the dotted green. You see what just happened there. Now, what is our domain? Let's look at the domain here. Okay, we can do any x value except for 0. So the domain is going to be negative infinity to 0 non-inclusive in union with 0 non-inclusive to infinity. Alright, well, let's do a graph here. Oh, wait, let's find our intercepts. So if we set x equal to 0 to try to find the y-intercept, we end up getting 1 over 0, which is undefined. We don't have a y-intercept. Now how about an x-intercept? You set all this equal to 0, you would just get 2x squared plus 1 equals 0. Well, there's no real solution for that. So you have no x-intercept either. So there are no intercepts. Let's go ahead and graph this. So if I put in 1 for x, I would get 3 over 1, which is 3. If I put in 2 for x, I would end up getting x is 4, so it'll approach the asymptote. Sorry, if I put in 2 for x, I'll end up getting, wait a minute. 1 was, so 2 times 4 is 8 plus 1 is 9 over 2. That's 4.5. I put in 3. Let's do one more. I'll end up getting, let's see, 2 times 9 is 18 plus 1 is 19 divided by 3. That would be 6 1/3. So here's roughly what that graph is going to look like. It rides the asymptotes. Your slant asymptotes and your vertical asymptote help guide the shape of the graph. Now, let's go to x equals -1. Alright, so that would give me 3 over -1, actually gives me -3. Let's go to x equals -2. So that would give me, let's see, 8 plus 1 is 9 over -2. That'd be -4.5. So it's going to do this number again here. That you got that vertical asymptote of x equals 0, and it helps guide the shape of your graph. So you get something like this. And this type of graph is very common when the degree of the numerator is greater than the degree of the denominator. Let's do another one with a slant asymptote. Then I want to talk about a couple special cases where you have a higher degree in the numerator than that of the denominator. All right. That's f of x equals x to the third all over 2x squared minus 8. So f of x equals x to the third over 2x squared minus 8. Well, clearly the denominator doesn't factor into the numerator, so we can go ahead and try to find some vertical asymptotes. If we set 2x squared minus 8 equal to 0, you would get 2 times x squared minus 4 equals 0, which would just give you x plus 2 times x minus 2 equals 0. So that means you have two vertical asymptotes that are going to occur when x equals both plus or minus 2. So we've identified both vertical asymptotes, plus and minus 2. Let's go over here and draw the second vertical asymptote. All right, now look at your equation here, okay? The degree of the numerator is exactly 1 degree greater than that of the denominator. That means you don't have a horizontal asymptote. Instead, you'll have a slant asymptote. If the degree of the numerator was more than 1 degree greater than that of the denominator, you wouldn't even have a slant asymptote. You might only have vertical asymptotes or no asymptotes at all. That is possible. Like if this were 2x squared plus 8, you wouldn't have any vertical asymptotes. But in order to find the slant asymptote again, let's do that long division. So this is going to end up being x to the third plus 0x squared plus 0x plus 0. All that divided by 2x squared plus 0x minus 8. 2x squared goes into x cubed 1/2 x times. So half x times 2x squared, that's x cubed, plus 0x squared, then minus 4x. So you end up getting a remainder of 4x. Well, we don't care about the remainder. We just don't care about the remainder. You only care about what you got that's not the remainder. So that means your slant asymptote is y equals 1/2 x. So you have a slant asymptote at y equals 1/2 of x. So let's go ahead and plot that. So 0, you still get 0. 1, you get 1/2. So let's see. 2, you would actually end up getting 1. 4, you get 2. 6, you get 3. 8, you get 4. 10, you get 5. All right. Let me just draw this very carefully here so we have an accurate representation. All right. Now at -2, you would get -1. At -4, you get -2. -6, you get -3. -8, you get -4. -10, you get -5. All right. Now going left. Alright, so there's the two vertical asymptotes and the slant asymptote. It's going to make a very interesting graph. So let's also look for intercepts. If you put in 0 for x, you actually do have an intercept at y equals 0. So at 0, 0, you have a y-intercept, and that would actually be your x-intercept too if you set the whole equation equal to 0. Both your intercepts are at 0, 0. So that's easy enough. Now your domain, it can be anything except x equals positive or -2. So your domain is going to end up being from -infinity to -2 non-inclusive in union with -2 non-inclusive to 2 non-inclusive in union with 2 non-inclusive to infinity. So let's put this together here. Let's say I put in 1. If I put in 1, I'll literally end up getting 1/10. I'll have a y value of 1/10, which would be really low, right about there. If I put in, well, I can't put in 2. Let's say I put in, what if I put in 1/2 for x? So let me take f of 1/2. What's that going to give me? That would give me 1/8 all over 2 times 1/4, which would be 1/2 minus 8, which would be 1/8 all over 1/2 minus 16 halves. That'd be over -15 halves. So that'd be 1/8 times 2 over -15. Wow, that'd give me -1/60th. Pretty close there. And then let's say I put in positive 1.5, which would be 3.5. what am I going to get? Well, that would give me 27/8 all over 2 times 9/4 would be 9/2 minus 16/2, which would give me 27/8 over negative 7/2, which would give me 27/8 times 2 over negative 7, which would give me negative 27/28. So darn near -1. So it looks like when I go this way, I'm going infinitely close to x equals 2. Now let's see what happens here if we pick -1/2. I'm actually doing the in-between piece first, you notice. So let's pick f of -1/2. So f of -1/2 is going to give me -1/8 all over, what's 2 times 1/4? That'd be 1/2 minus 16/2. So that's going to give me -1/8 all over -15/2. Well, the negatives are gone. You would just get 1/8 times 2 over 15. That would give you positive 1/60th, which would barely be right here. If I put in -1, I'll get -1 over 2 minus 8, which is -6. I'd end up getting -1/6, a little bit higher. If I put in -3/2, it would get even higher. So something very interesting occurs here. Look at this middle piece. Look at that. It actually does cross a slant asymptote, and you can have that. Sometimes you will have that. It can cross slant asymptotes, but not always. Alright, so what about to the left of your asymptotes? Let's go to the left of -2. So let's say I put in x equals -3. F of -3 is going to give me -27 all over 2 times 9, which is 18 minus 8, that's 10. That'd give me -2 7/10, which would be about right there. Let's say I put in -4. Well, that's going to end up giving me -64 all over 32 minus 8, which is 24. That would give me -2 16/24, which would be -2 2/3, which is even lower yet. That's even higher. And then if I put in -5, I get -125 over 48. So yeah, it would continue going infinitely downward like this. This is roughly what your graph is going to look like. And then if you come over here, do the same thing, you would get the positive of those values. So if I put in f of 3, I would get 27 over 10, which we determined was 2 7/10. So yes, your graph is going to look a lot like this. So to the left and right of the asymptote, your graph behaves, but in the middle, it actually crosses a slant asymptote, which does sometimes happen. All right. Just 2 more I want to do. These are both special cases. You're going to see what I mean by special. let's say I have f of x equals x squared minus 1 over x plus 1. So f of x equals x squared minus 1 over x plus 1. Well, it's pretty apparent we can factor this, right? What's that going to factor into? It would just simply equal x minus 1, which would give you a line. It would look like we're done, no asymptotes or nothing. That would be true, except though that x plus 1 factored out, you still have to account for the original equation. So what does that mean? You don't have a full-fledged vertical asymptote. What you have is what's called a hole, where x equals -1. You have a hole where x equals -1. So if you put in, you want to find the coordinate of your hole, put in that -1 into the factored equation. You get -1 minus 1, you get -2. So at the point -1, -2, you have a hole. It's just simply not defined there. You don't have a whole vertical asymptote, you just have a hole, which is, in calculus, we'll call a removable discontinuity. So what you're going to have is a line, except at -1, 2, it's not defined. So when x is 0, you would get -1. 1, you get 0. 2, you get 1. I think we get the idea. Let's see, at -2, you get -3. -3, you get -4, and so on. So you just have a line with a gaping hole in it at the point -1, -2. But otherwise, your domain and your range is literally the set of all real numbers with no asymptotes. Now let's do one more here. This one may change a little bit. Let's say we have f of x equals x squared plus 3x all over x squared plus x minus 6. Well, it looks like they're the same degree, right? But you can factor this. Let's just factor both the numerator and denominator. This would turn into x times x plus 3 all over x plus 3 times x minus 2. This is just the factored form of the original. Well, what do you notice? Of course your x plus 3's cancel out. You're left with simply x over x minus 2. Which is fine. So for sure you're definitely going to have a full-fledged vertical asymptote at x equals 2, right? However, you also have to look at the original factored form. Even though the x plus 3 is factored out, you still have to set x plus 3 equal to 0. What's going to happen is you'll have a hole when x equals -3. You won't have a full-fledged asymptote, you'll just have a hole. So if you want to find the coordinate, put in -3 into the new factored form, you'd have -3 over -5. So that would be at the point -3 positive 3/5. That would be your hole. So let's draw the asymptote and the hole. The hole, let's draw the asymptote at x equals 2. Then we can identify the hole at -3, 3/5, which would be about right there. There's your whole. Now, what about a horizontal asymptote? You can use the factored form, and you would get a horizontal asymptote at y equals 1. So, you have a horizontal asymptote located at y equals 1. So let's draw the horizontal asymptote. And now we can just go ahead and graph this. And it's going to look like a typical rational function, except you have a hole. Oh yeah, so both your intercepts, you set this equal to 0, you would get both x and y intercepts at the point 0, 0. So here's roughly what your graph is going to look like. It looks almost like a normal rational function, except you have a hole at that -3 3/5. Then let's put in 4. You would get 4 over 2, which is 2. And your graph is going to look like this. So it looks like the graph of a normal rational function, except with a hole. That's the difference. So that's it for graphing rational functions. Next lesson, we're going to start the unit, and it's a short unit, on exponential and logarithmic functions. The very next lesson will be exponential functions and their graphs. So I hope everyone has a great day. Take care.